In this paper, we present GroomGen, a high-quality generative hair model using hierarchical latent representations. Our model can generate diverse hair models by randomly sampling in the latent space. It can be used as a hair creation tool for technical artists, or a prior constraint in hair capturing. The input of our system is simply a random vector of 512 dimensions drawn from normal distribution. The output is a high-quality hair model of 180,000 hairs with expressive details. Inspired by the standard hair grooming procedure in the industry, we design our system in a hierarchical structure. For a hairstyle, the most basic element is a hair strand. At a higher level, a sparse set of guide hairs are used to represent the overall shape of a hairstyle. Finally, a complete hair model is created by populating the guide strands. Our system covers the 3 levels of a hair model with 3 modules. At the strand level, we adopt a strand variational autoencoder model to encode the shape of a strand. At the hairstyle level, we propose a hairstyle variational autoencoder to learn the hairstyle latent space. Finally, we introduce the hybrid densification step that densifies the sparse guide hairs into dense hairs. We first introduce the strand variational autoencoder. At the strand level, we first adopt discrete Fourier transformation to convert a strand from the spatial domain to the frequency domain. Then, the encoder of the strand VAE takes the frequency components as input and compresses them into a strand latent code. Symmetrically, the decoder learns to decode the latent code back to the frequency spectrum. With the pre-trained strand VAE, given a hair model, we can encode each hair of it from the Euclidean space to the strand latent space. At the same time, we unwrap the scalp area of the head mesh into a UV map and embed the latent code of each strand into the corresponding pixels. In this way, we can describe a hairstyle with this latent map representation. The resolution of the latent map decides the number of hairs. In this paper, we use 2 different resolutions. For a dense hair model with around 30,000 hairs, we use a high-resolution latent map. For sparse guide hairs, we use a low-resolution one. Now we come to the second level of our hierarchical representation, the hairstyle level. At this level, a hair model is represented by sparse guide hairs. These guide hairs are encoded into a low-resolution latent map. We train a hairstyle variational autoencoder to establish a hairstyle latent space. The hairstyle VAE contains an encoder part and a decoder part. The encoder learns to encode low-resolution latent maps into a latent vector, while the decoder learns to reconstruct the latent maps from the latent code. At inference, only the decoder part is kept. The latent codes are drawn from normal distribution. Here, we emphasize again that the hairstyle variational autoencoder only generates low-resolution latent maps, which can be decoded to a set of sparse guide hairs. Due to the local similarity of human hairs, a few guide strands are already sufficient to describe the overall hair shape. This compact representation makes the task easier. To get dense hairs from sparse hairs, we introduce the third component, hybrid densification. In this step, we generate 180,000 hairs from 400 guide hairs. The first part of our hybrid densification is formulated as a super-resolution task. We first decode the low-resolution latent map with the strand VAE decoder into the frequency domain. Then, we adopt a novel neural upsampler to upsample the low-resolution strand map into a high-resolution one. This step increases the resolution by 9 times, and the number of strands is increased from 400 to 30,000. The upsampling is followed by the heuristic refinement. It adds fine details to the hair model based on user control, and increases the number of hairs to 180,000. Now we have explained the 3 modules of our system. At inference, we start from a random hairstyle latent code. It is first decoded into a sparse latent map by the hairstyle VAE, and then decoded by the strand VAE, and finally densified in the hybrid densification step. The hairstyle latent space of our system is well constrained. As a result, generating new hairstyles is easy as drawing random vectors from normal distribution. All the results demonstrated currently are generated by our model automatically. Here we demonstrate reconstructed hair models based on the same set of guide hairs but different user parameters. The user can control the fine details by specifying the number of wisps and hair stickiness. In this page, we demonstrate various combinations of the user parameters. Moreover, thanks to the latent space, we can perform hairstyle interpolation by linearly interpolating the latent codes. As another interesting application of the Strand latent space, we additionally trained a neural simulator that performs quasi-static simulation of hair strands under different gravity directions. Specifically, given a strand geometry in Euclidean space under standard gravity direction, the model learns to predict the shape deformation with another given gravity direction. To do this, we first use the strand variational autoencoder to encode the strand into the latent space. Then, the latent code, the position of the strand root, and the gravity direction are fed into the neural simulator. The output of the neural simulator is the latent code of the deformed strand, which can be decoded back to the Euclidean space by the strand variational autoencoder. In this way, we can simulate hair deformation under different head poses by changing the gravity direction. The simulation is visually plausible, and our method is 1,000 times faster than a conventional simulation. The high efficiency renders the neural simulator an ideal alternative for lightweight preview. Thank you for watching.